Hello, everyone. Let's begin our discussions of different topics. This is by far my favorite part of this course. I really enjoy discussing these types of things with students and with you guys, actually with anybody. Unfortunately, we're not really going to be able to discuss so much since we're not in class. Okay, and instead of discussions, then I want to turn this portion of the class into more of reflections. Okay, so I want you to reflect on these topics, think about them, read and watch the material that I provide for you, and then write the 3 to 5 paragraph response or opinion on the topic and submit it back through Canvas, like I mentioned in the previous email. Okay, if you want more information on that, you can email me or you can look through that email. It's pretty straightforward. But for now, I'm going to give you a brief introduction on what climate change actually is, and then I recommend you go and you do a little bit of digging on your own to learn a little bit more about this topic. Okay, climate change, what does it actually mean? To talk about climate change, we have to start out with the energy that the Earth receives. Okay, now the energy, or most of the energy that the Earth gets, 99.9% of the energy that the Earth uses or absorbs comes from the sun in the form of light. What is light? Light is the energy that's being released by the nuclear processes in the sun. And light is considered to be basically a tiny packet of energy. And each of these tiny packets of energy are called photons. And each of these photons can have a different amount of energy. And this energy is related to something called its wavelength. You can tell the energy of a photon by looking at its wavelength. And the sun gives off all different types of photons. The spectrum that the sun gives off, which is all of the different energies of photons that the sun gives off, spans from the ultraviolet range to the visible light range and to the infrared range. And we can actually sense all of these wavelengths. Okay, even though you can only see the stuff in the middle, you can sense all of them. For example, ultraviolet, you guys know, I'm sure, if you sit outside too long at the beach or sit outside too long in this beautiful weather that we've been having in East Tennessee lately. I don't know about wherever you guys are. We've been having some really nice weather here, and I spent a little bit too much time outside one day, and I got a sunburn. Yep, I got a sunburn. So I'm sensing these ultraviolet photons that are coming from the sun, and I'm sensing them by receiving a burn, an actual sunburn from these photons hitting my skin and interacting with the tissues of my skin and actually damaging them in some way and giving me a burn. Okay, so that's not so great. We don't really want to have a sunburn, but we can still sense them. Every time, by the way, every time I get a sunburn, I'm like, sensing UV rays. Everybody loves me for it. I tell you what. Next is a slightly lower energy than ultraviolet is called visible light. And this is the colors that we can see, starting red, orange, yellow, blue, indigo, and violet. These are all the colors that we can see, the colors of the rainbow. They come out of the sun. All right, and the way that we sense or we see the sun, obviously we see it as a white color. Don't look at the sun. I don't recommend that. But if you ever do, you'll notice that it's white. And this is because all of the colors are kind of mishmashed together. And when you put all of the colors together in terms of light, you get a white light. And then there's another form of light that we can't see directly with our eyeballs, but we can sense it. This is called infrared energy or infrared photons, infrared light. And this feels warm. We can feel the warmth on our skin if we are under an IR lamp of some sort. This is why the sun feels so warm. We can stand out in the sunshine and feel the warmth radiating us. That's one part of that is because we're actually absorbing some of the visible light and ultraviolet light, and that's causing us to warm up. But certainly it's also because there is some infrared light coming from the sun as well. Okay, and this is a little bit lower in energy than visible light and ultraviolet light. And if you keep going to lower energy side, you get to radio, microwave, etc., etc. That's what they're using to communicate. That's what your cell phone is using to communicate, radio waves. That's what your Wi-Fi router. That's what your Bluetooth connection. That they're all using radio waves. And you can't really cook instant microwave popcorn without using your microwave. That is definitely a microwave oven is using these photons. It's using a form of light to basically excite different transitions within water, and it heats the water up. So it boils water from the inside, and that's why it pops corn. You're actually boiling water on the inside of the kernel, and then the kernel is exploding because the water is heating up and turning into gas. Isn't that cool? Okay, so that's radio and microwave. It's in the lower energy spectrum. And if you go to higher energy spectrum than ultraviolet, you get things like X-rays and gamma rays, stuff like that. Not so nice. But thankfully, not much of that comes out of the sun. Okay, so this is all the energy that's coming out of the sun and hitting the earth. Now, the important thing about the earth is that it has what's called an atmosphere of gases that are trapped around the earth, and they're held to the earth by gravity. So gravity holds these gases close to the earth, and as a matter of fact, as you move further and further away from the earth, the amount of gravity drops off, right? You're moving further away, the amount of force that you're being pulled towards the earth drops off, and the amount of gases that are around you also drops off. So there's a gradient of gases depending on how close you are to the center of the earth. For example, if you were to hike up to the top of Mount Everest, there's not enough oxygen up there to actually allow you to breathe and to get enough oxygen into your body. So the hikers that go up there often have to bring oxygen packs, and this helps them supplement the fact that there's really just not enough oxygen. There's not enough air in general if you go up to 30,000 feet. Okay, so the atmosphere surrounds the planet. And the atmosphere is composed mostly of nitrogen. So N2 gas is the most common gas within the atmosphere. Next comes oxygen at around 21%. And then there's argon at about 0.9%. And then there's a bunch of trace gases that are around 0.1% of the atmosphere. And these trace gases include mostly carbon dioxide. So it's 93.5% of that 0.1% is carbon dioxide. And then there's a bunch of other stuff. Okay. So carbon dioxide is the most abundant trace gas. And, well, actually, let's come back to this idea of having an atmosphere. Okay, so first I want to talk about the greenhouse effect. Okay, so here, remember, carbon dioxide is kind of, it's close to being it's the most abundant trace gas is what I want to say. Remember that. And it's in the atmosphere. Next, the greenhouse effect. What does it actually mean? The greenhouse effect allows us to drastically increase the temperatures inside some sort of enclosed space. Okay, and the way that this works is you have plastic or glass walls on this greenhouse. And these plastic or glass walls are transparent to visible light. So they allow light to come through from the sun, visible light to come through. And this visible light comes through and is absorbed by the plants and the earth, or anything within the greenhouse, really. They absorb that energy. And then once they absorb the energy, they re-release, or they emit some of that energy as a less energetic photon. Okay, so when things heat up in the sun, they re-emit that energy as an IR photon. So when something gives off heat, it's literally releasing infrared photons. And the problem, or I guess in this case, the great thing about these glass or plastic shields is that they are not transparent to infrared light. So the plastic actually reflects back the infrared light into the grow tent, or into the greenhouse in this case, which causes these IR photons to kind of bounce around and get reabsorbed by the plants and the earth, and eventually it leads to a drastic increase in the temperatures inside the tent. So you can create a very warm environment inside some greenhouse by simply allowing the visible light in and not allowing the infrared light back out. The Earth works in much the same way. There's an amount of light coming in from the sun, and this is kind of a confusing graph in terms of the numbers. Don't worry about the numbers so much. Just look over on the left. And actually, can I? Well, I'll do that another time. Never mind. Look over on the left, and you see the beam of light coming from the sun. This is representing the amount of light that's coming from the sun that's hitting the Earth, impinging on the Earth. A certain amount of it gets reflected by the atmosphere and reflected by the clouds. A certain amount of it gets absorbed by the atmosphere, and a certain amount of it makes it all the way through all of those things and is finally absorbed by the surface of the Earth. Okay? Once it's absorbed by the surface of the Earth, some things can happen. Well, first of all, some of it's also reflected by the Earth. Once it's absorbed by the Earth, some things can happen. This energy, this heat energy, needs to be re-released somehow. The total net energy can't ever be plus or minus. You have to release all of the energy that you absorb in some way or form, or you have to use the energy in some way or form. So this energy is getting released or emitted by the surface, and the way that things that are things that heat up, the way that they release that heat or the way that they release that energy is by infrared radiation, just like in the greenhouse effect. Now, what's happening here is instead of having a glass or plastic shield around the greenhouse like you would with a greenhouse, the Earth has the atmosphere. Now, the atmosphere, it turns out, is transparent to visible light, but it is not transparent to infrared light. Just like a greenhouse plastic or glass panel, it absorbs that infrared radiation, or it reflects that infrared radiation back to the Earth. Some of it is radiated out into space, and some of it is re-radiated back into the Earth. And this is what causes the overall heating effect of the Earth. Now, this is not necessarily a bad thing, right? Without this atmosphere helping the Earth create this nice, warm, humid environment, life would not exist. We would be an empty, void vacuum of space, essentially, like Mars, and we wouldn't have any sort of life present on us. So this atmosphere, or this greenhouse effect, is really helpful for the continuance of life on this planet. Now, there are several gases that contribute to greenhouse effects on the Earth, and these gases turn out to be transparent to visible, just like plastic and glass, but not transparent to the infrared. So they act just like the plastic and glass covering of the greenhouse. The largest contributor currently is carbon dioxide, and then there's others, methane and nitrous oxide. Like I mentioned, warming the planet is definitely a necessary thing, and this provides some way of the Earth achieving some sort of homeostasis, meaning that the temperature of the Earth doesn't fluctuate wildly between when the sun is up and when the sun is down. It kind of keeps a constant temperature even throughout the year. It enables life to survive on the planet. But is it too much of a good thing? Okay. Over the last 300,000 years, we've been able to measure the concentration of CO2. Let me see if this, the concentration of CO2 in the atmospheres and the temperature of the Earth, the average temperature of the Earth, by taking ice core samples from the Antarctic region. And essentially what this is they're drilling down and gathering a rod of ice deep into the ice in Antarctica, and each of these striations within the ice, as you can see here, represent different years, and they can analyze each of these different years much like you would analyze the rings of a tree. So they can look at each of these rings of ice formation, and they can find carbon dioxide concentrations in the trapped air pockets within the ice. They can carbon date the CO2 to provide the age of that ring, and they can find the average temperature of the time by looking at the microscopic ice crystal formation. So basically, how the ice crystals look under a microscope determines how cold that year was, and they can determine all of this by looking at these ice cores. And they've been able to go back a significant amount of time, almost 350. Yeah, I think it's around 350,000 years ago. And they can see the average temperature in Antarctica there on the y-axis in degrees Fahrenheit. And you can see it hovers somewhere around negative 72 degrees Fahrenheit, which is pretty cold. Now, there are peaks and valleys all throughout this time period. And what you see that's very interesting are these two graphs kind of track each other. So we have a red graph, which represents the temperature, and a blue graph, which represents the CO2 concentration in the atmosphere. And they're generally tracking each other for the past 350,000 years until you get to modern times in the past 100 years or so, where CO2 has gone absolutely crazy and has gone above levels we've seen for the past 350,000 years. And we're not really sure what's going to happen with the temperature. So that's the big question. What's going to happen with the temperature? Is the temperature going to rise because this greenhouse gas is increasing in the atmosphere? Or are we going to see something that we haven't seen in the past 350 years? 350,000 years. So what's going to happen here? What's going to happen with the Earth's temp? This is the whole question surrounding climate change. Is that the assumption here is that actually the Earth is going to start heating up because CO2 concentrations in the atmosphere are increasing, so we're increasing the amount of greenhouse gases in the atmosphere, and therefore we must be increasing the temperature of the planet, simply because there's going to be more molecules absorbing that infrared light and re-radiating it back to the Earth. So where does CO2 come from? There's many different places that CO2 comes from. I guess the main one that climate change is interested in is our combustion reactions, where carbon-bearing molecules such as methane or gasoline or diesel or ethanol or methanol or even wood, when you burn them in the presence of oxygen, they create CO2. Okay. But wait, you might be saying, ethanol is supposed to be a green alternative to gasoline. Have I been lied to? No, you have not been lied to. And this all has to do with the circle of life, or the carbon circle. What's available in the carbon dioxide cycle, as it's called. As you know, producers absorb energy and nutrients from their surroundings, from the environment, and they make their own food. So here I'm showing a picture of a plant. It's absorbing sunlight through photosynthesis. It's converting that sunlight into chemical energy, and then it's using that along with water, and it breathes in carbon dioxide from the atmosphere to actually produce sugars or structure within themselves. So the plant is actually growing itself using water, carbon dioxide, and sunlight. So it produces sugar, fiber, everything that a plant needs to grow. And interestingly, what it's doing is it's sequestering that carbon dioxide from the atmosphere, and it's using that carbon to build itself up. So plants contain an enormous amount of carbon, and when you burn them, you release that carbon dioxide. However, that carbon dioxide is already part of the carbon dioxide cycle that's happening within our environment right now. So there's a certain amount of carbon that's available on the surface of the planet. And this is all considered to be part of the carbon dioxide cycle. So if you take, for example, corn, and you ferment it to form ethanol, and then you burn that ethanol to produce CO2 and water, you are not changing anything about the carbon dioxide cycle, because you are simply releasing the CO2 that was sequestered by the corn. So you are not changing the carbon dioxide cycle, and therefore this is said to be carbon neutral. Okay, and the carbon cycle is very similar to the circle of life here that I have shown here. So producers absorb sun and water, and then they get eaten, blah, 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 all the way up to fungi, and then it goes back around in the food chain. It's very similar for the CO2 cycle. CO2 comes into the plant along with sunlight and photosynthesis, and it allows these organic plants to grow, essentially. So they take in this carbon and they turn it becomes organic carbon. And then eventually they can decay and release that CO2 back into the atmosphere. Okay, and animals can eat the plant and also release that CO2 back into the atmosphere. But another bit can also occur, and this is where organic carbon is actually captured underneath rock, deep underground, and it's fossilized, and it's turned into fossil fuels. This is what fossil fuels come from, are organic matters that have been trapped underground under extreme pressures and temperatures for a long period of time, and they turn into what we call fossil fuels, oil, coal, stuff like this. This is all biological or organic life at one point, and it has been turned into fossil fuels by sitting in this high pressure environment underground for a very long time. The important thing is that these biological or organic materials are no longer part of the CO2 cycle. If they get stuck underground, they are not part of our current CO2 cycle. They could have been part of this CO2 cycle at one point, and as a matter of fact, they must have been part of the CO2 cycle at one point, but they are not currently part of the CO2 cycle. When we take these fossil fuels, and we burn them by some sort of, driving your car, using gasoline, factories burning coal, factories burning methane, etc., etc. It's a nice cheap form of energy. However, what we're doing is we're taking all of that carbon that's been stored underground for so long, and we're releasing it into the atmosphere. So we are releasing it into the CO2 cycle when it shouldn't be in our current CO2 cycle. And as you saw from that graph previously, for the past 400 years, it for sure has not been 400,000 years, it has not been part of our CO2 cycle. So we're releasing all of the CO2 into the atmosphere that shouldn't be there. And ostensibly, what we think is going to happen here is that it's going to increase the temperature of the Earth. And what I'm showing here, I'm going to restart this because it's really cool. Right down here is, at the very bottom of this, is the global temperature from 1880 to 2018. And the different colors, red and yellow, indicate more heat, and blue indicates less heat. Okay, so starting around 1880, you see that the temperature of the Earth slowly grows and slowly increases over time. And we've seen a very pronounced warming effect over the past 100 years or so. Okay, and towards the end there. Right, and as at the same time, we've actually also seen the carbon dioxide levels increase as well. And so the question here is, right now, after we've done a lot of burning of fossil fuels in the past 150 years after the Industrial Revolution, what's going to happen with the global temperature now? We are in a region where we've never been before, and we don't have data to see what's going to happen here. We can predict what's going to happen, and the prediction is that the Earth is going to heat up by a drastic amount. The question is, how much is it going to heat up? How terrible is it going to be for us as a species? How terrible is it going to be for the Earth as a general system? These are all questions that we need answers to, and climate science seeks to address that problem. Okay, so simply put, climate change is all about the expected effect in the climate that will come about because of increased levels of CO2. These increased levels of CO2 come about because humans have been burning stuff that's been stuck underground, CO2, or carbon sources that have been stuck underground for millions of years, and suddenly we're releasing this into the atmosphere. So this is somewhat unprecedented. We don't know what's going to happen. We can guess, we can make a very good guess at what's going to happen, which is going to be that the Earth will continue to heat up if we do not curtail our CO2 emissions. Okay, so that's climate change in a nutshell. Please make sure to look at the other sources that I've posted on Canvas. And I hope that you guys get something out of this. And if you have any questions, please feel free to email me or chat me on Google. Either way. All right. Take care. Hope you guys have a great day.